Hello everyone. In the previous class, we have discussed about amplification with BJTs. In today's class, we are going to discuss briefly about the BJT fabrication. So, in this class, we are going to use few technical terms, which are the different types of processes which will be covered in detail in the module number 5. But as far as in this topic those steps are used here or those processes are used, we will just define what are those terms. So let us review a simplified version of how to make a double polysilicon self-aligned NPN silicon BJT. So here we are going to discuss about the double polysilicon self-aligned NPN silicon made BJT, that is bijunction transistor. So this is the most commonly used technique for making BJTs for use in an IC, that is integrated circuit. As we know, in the IC, that is in the integrated circuits, they are made up of number of transistors. So BJTs also can be used in the IC. So this is the most commonly used technique for making the bipolar junction transistor for use in a integrated circuit. So use of an NPN transistor is more popular than PNP devices, as we know, because of the higher mobility of the electrons compared with the holes. So we know that the electrons are capable of moving faster than the holes. So we use NPN transistor more than the PNP transistor. So the first step in the BJT fabrication. So this figure shows the process flow for double polysilicon self-aligned NPN BJT. So the figure shows the N plus buried layer formation. So here a P type substrate, down you can see P minus. So that is this P type silicon substrate is oxidized and windows are defined using the photolithography. So here oxidation, the term oxidized, it is also called as a thermal oxidation. So the meaning of this one is, it is a process of heating up the wafer in very high temperature. So the wafer is going to be heated in a very high temperature in order to enhance the chemical process, to make them some chemical process. So by doing this, we are going to form, for example, the thermal oxidation of the silicon into the silicon dioxide, that is Si to SiO2. That is nothing but the oxidation process. And one more term we have used, that is a photolithography. So photolithography means it has three different terms: photo, litho and graphy. That is, photo means light, litho means stone in Greek, and graphy means writing. So here the patterns that is corresponding to a complex circuits are formed on a wafer using this process, that is photolithography. That is, it is the process of transferring the geometric shapes on a mask to the surface of a silicon wafer. That is called as photolithography. So a p-type Si substrate is oxidized, windows are defined using a photolithography, and they are etched in the oxide. So here the one more term, etching. So etching is a process in which we are going to remove the unwanted parts of the layers like silicon dioxide, silicon nitride or metal in the various steps from the surface of the wafer in order to form holes for diffusion or electrical interconnection and some other purposes. So that is nothing but the etching. Etching is nothing but removal of the unwanted layers is called as etching. So the p-type Si substrate is oxidized, windows are formed, and using a photolithography and etched in the oxide. So using the photoresist means it is a light sensitive material used in a photolithography to form a pattern coating on a surface. So it is what? It is a light sensitive material that is used in the photolithography process. So using this we are going to form a patterned coating, that is whatever the circuit that we need to define on a wafer, that is nothing but called as pattern. So pattern coating is done on a surface. So it has again two different type of photoresist, positive photoresist and negative photoresist. All these things we are going to be covering in the module number 5. So using the photoresist and the oxide as an implant mask, a donor with a very small diffusivity in the silicon such as As, that is arsenic, or Sb, that is antimony, is implanted into a open window. So here implanted means diffusion or ion implantation is going to be used here. So it is a process of doping, or it is a method of doping. It is also a very high temperature process in which dopants are used, such as the arsenic, antimony, boron, phosphorus, etc. into the patterned wafers. So antimony or arsenic is implanted into the open windows to form a highly conductive N plus layer. Subsequently, the photoresist and the oxide are removed. So this process is called as etching, and a lightly doped N-type epitaxial layer is grown. So as you can see from the figure, a photoresist is grown, As is used as an implant, SiO2 layer is formed. All that you can see in the figure. So the photoresist and the oxide are removed and a lightly doped N-type epitaxial layer is grown. So during the high temperature growth, the implanted N plus layer diffuses only slightly towards the surface and becomes a conductive buried collector, that is called as subcollector, that is shown in the figure, buried layer, or it is also called as a buried collector or subcollector. The step number 2. So in this figure, the figure shows the N epitaxy followed by a LOCOS, LOCOS, LOCOS isolation. So for the integrated circuits involving not just the discrete BJTs, that is bipolar junction transistors, but many interconnected transistors also. So there are some issues involving the electrical isolation of adjacent BJT in order to ensure that there is no electrical crosstalk between them. So as there are number of BJTs are going to be present, so these are not just the discrete BJTs, there are number of interconnected transistors are also will be present. So if unknowingly or unwantedly, if they are adjacent BJTs connect each other, then there will be a crosstalk. So to avoid this one, there is no crosstalk between them. We need to have an isolation. So such isolation can be achieved by LOCOS to form a field or isolation oxides after the boron, that is B, channel stop implant. So there is another isolation scheme that is particularly well suited for high density bipolar circuit that involves the formation of the shallow trenches by RIE, that is reactive ion etching. So this RIE process will be discussed in detail in the module number 5. So the formation of the shallow trenches by the reactive ion etching backfilled with the oxide and polysilicon. So in this process, a nitride layer is patterned and used as an etching mask for an anisotropic etch of the silicon to form the trench. Oxidation inside the trench forms an insulating layer, and the trench is then filled with the oxide by the LPCVD, that is the low pressure chemical vapor deposition. So this process is also going to be discussed in module number 5. Then the step number 3. So here in this figure it shows the base emitter windows definition, and there is an optional masked sinker implant into the collector contact region. So here the N plus subcollector layer. So the N plus subcollector layer guarantees a low collector series resistance when it is connected subsequently to the collector ohmic contact. Sometimes through the use of an optional masked deep N plus sinker implant or diffusion only in the collector contact region. The lightly doped N-type collector region above the N plus subcollector in the part of the BJT where the base and emitter are formed, that are going to be ensure a high base collector reverse breakdown voltage. A polysilicon layer is deposited by the method called as LPCVD, that is low pressure chemical vapor deposition, and doped heavily P plus with boron either during a deposition or subsequently by an ion implantation. So as we discussed, ion implantation is a method of doping. It is a very high temperature process in which the dopant is used. So an oxide layer is deposited next by the LPCVD, that is low pressure chemical vapor deposition. Using photolithography with the base or emitter mask, a window is etched in the polysilicon oxide or oxide stack by the reactive ion etching. So this is the step number 3. Step number 4. So it is a intrinsic base implant using self-aligned oxide sidewall spacers. So that is a heavily doped extrinsic P plus base. So as you can see here in the figure, there is a P plus base. A heavily doped extrinsic P plus base is formed by diffusion of boron from the doped polysilicon layer into the substrate in order to provide a low resistance, high speed base ohmic contact. An oxide layer is then deposited by the LPCVD, which has the effect of closing up the base window that was etched previously, and boron is again implanted into this window. This base implant forms a more lightly p-doped intrinsic base through which most of the current flows from the emitter to the collector. The more heavily doped extrinsic base forms a collar around the intrinsic base and serves to reduce the base series resistance. And this is a final step, step number 5. So here the self-aligned formation of N plus emitter as well as N plus collector contact is shown. So here finally another LPCVD, that is low pressure chemical vapor deposition oxide layer, is deposited to close up the base window further, and the oxide is etched all the way to the silicon substrate by reactive ion etching. leaving the oxide spacers on the side walls. Heavily N plus doped, that is typically with the arsenic. Heavily N plus doped polysilicon is then deposited on the substrate. Then it is patterned and etched, forming polysilicon emitter, that is we can call it as polyemitter and collector contacts. Arsenic from the polysilicon is defined into the substrate to form the N plus emitter region nested within the base in a self-aligned manner, as well as N plus collector contact. Self-alignment refers to the fact that a separate lithography step is not required to form the N plus emitter region. So we have again and again used the self-alignment. So the meaning of that one is a separate photolithography process is not required here to form the N plus emitter region. So these are the 5 steps that are used in the fabrication process. So in detail we are going to discuss the fabrication process, the different processes that are involved, like photolithography, reactive ion etching, chemical vapor deposition, thermal oxidation, etc. in the module number 5. Thank you for watching the video.